Now in this video, we're going to talk about Paxos. We're not talking about going on vacation to Greece. We're talking about consensus algorithms in distributed systems. To understand what a consensus algorithm is, it's best to start with an example. Let's say you're sitting at your computer and you're talking to your bank and you're either giving them your money or you're taking out some of your money. In either case, you want to make sure that your bank never forgets your bank balance even when you do these transactions to your account. Your bank also cares a lot about this. So what do? They may replicate your bank balance across more than one computer, on the assumption that computers won't fail that often, but when one fails, they can just have you fail over to one of the backup computers and you can keep on working and they don't forget how much money you have. So they're assuming that a computer can fail at any time, but they also are assuming that their replicas of the system are all in agreement and they all have the same balance represented at all times. And so solving that problem requires you to solve the consensus problem so that any value that changes on one of the computers is reflected on all of the other computers and they're in agreement. You may be saying to yourself, I know how banks work. They don't use a consensus algorithm to replicate my balance across a cluster of redundant nodes. They simply use database replication. And how my database replication works is I just talk to a primary server, my database server. I do my transactions there. And all of the transactions that happen form log entries, which then get shipped to backup servers. And those backup servers replay the transactions and create a nice copy of what changed in the original database. And that's true. This is a common solution to the problem. But it has a couple of issues. Either when the primary machine fails, you lose the most recent transactions because they haven't been copied to the backup servers yet. Or when that machine fails, you have some mechanism for securely copying those transaction entries, those log entries, but it takes time to replay them on the backups so that the backups can catch up, and then you get downtime in your system. Either of those may not be desirable properties, and if they're not, you build a more reliable system that uses a fully synchronous replication scheme across all of your primary and backup database servers, and at that point, either your database system implementers or you have implemented some form of consensus algorithm so that all of your database replicas are in a consistent state with each other. So let's talk about how you go about building such a system. Now, we're talking about Paxos today, which is one of the first algorithms that solves the consensus problem. And Paxos has got a reputation, which is it's gotten a reputation for being one of the hardest things to learn in distributed systems. And hopefully, by the end of this video, you're convinced that that's not actually true. Basic Paxos, which is the truly unique part of the Paxos algorithm as described, is not that complicated. It's fairly easy to understand. It's a series of messages that go between the computers, and it keeps the computers in consensus. And as a matter of fact, this basic Paxos algorithm is the revolutionary part of Paxos. Back in the 1980s, there were a bunch of researchers that were working on the consensus problem because they wanted to figure out, is it actually possible to get a bunch of computers to agree at all times? And there were real systems that did this, built on research by Nancy Lynch and Barbara Liskov, that actually implemented consensus solutions. Great, problem solved, right? Well, Leslie Lamport came along and said, yeah, well, we've got practical solutions that seem to work, but no one's built a rigorous mathematical foundation that proves that these things can work. And I'm sort of convinced that, you know what, if I try and come up with the math, I'll be able to prove that it actually can't be done and cover all of the cases and all of the failure modes. And so Leslie Lamport set to attack this, and he actually did the opposite. He built a rigorous mathematical foundation upon which he built the Paxos algorithm that showed that it actually could be solved. And she's like, great, I'm going to publish a paper. He published a paper, unfortunately, that had a clever story wrapped around it about some parliaments in the Greek islands of Paxos and how they came up with a distributed solution to passing laws. And he tried to get this published, and the reviewers got sort of confused. They were confused by the story, and they weren't able to read through it and see all of the math and truly understand the brilliance of the math behind it. And so as a result, this paper actually took 10 years to get published, and it wasn't until the late 90s that it was finally published in a conference. Even once it was published, people got confused by the story. the story of all these parliamentarians running around, and they weren't able to clearly understand the math. And so Lamport published a simplifying paper in 2001 called Paxos Made Simple. And I have to admit, I've read the Paxos Made Simple paper again and again and again, and it is simpler than the original paper, but it is still somewhat confusing to me. And the reason is because the problem the paper is trying to solve is they're trying to show that, hey, look, it's possible to do consensus, and here's how you prove the math. Which is a cool thing, but if what you're actually interested in is understanding how you build a real system that solves the consensus problem and builds up a system on top of that, this paper is a little bit more hand-wavy in that domain and solving a bunch of the other problems you need to solve to build a real system, such as how do you do more than one transaction, one after another. The paper proposes something called multi-Paxos to do that, but it's actually a lot more complicated than it seems like it needs to be. And so if you're actually trying to build a real system, some follow-on research has gone into how to make real systems easier to understand, easier to debug, and easier to implement. And some researchers from Stanford came up with an algorithm called RAFT, which is vastly superior to Paxos when it comes to implementation complexity. And so I highly recommend that you learn that too. But if what you're trying to do is understand existing Paxos algorithms or understand the basic idea of how you get computers coming to consensus, it's still valuable to learn Paxos. And so we're going to go over that today. In order to understand how Paxos works, you have to understand what it's defending against, the failure model. What failures are allowed and what failures are disallowed when you are building a Paxos system. This isn't a true Byzantine fault model. We don't allow anything and everything to go wrong. Instead, we're assuming fail stop. We're assuming that you have more than one computer and that some of those computers can die at any time. And Paxos will keep on working even in spite of those computers dying. So you may ask yourself, how many computers can die? And the answer is, as long as more than half of your computers are still running, Paxos will keep on working just fine. And so this is why when you look at a Paxos setup, people usually use an odd number of computers. They use 3 computers if they want to tolerate one failure. They use 5 computers if they want to be able to tolerate 2 simultaneous failures, and 7 computers for 3, and so on and so on and so on. You assume that the computers can die, and when they die, they stop working. They stop sending out messages to the rest of the network. You also have to make another assumption, which is when a computer dies and comes back alive again and rejoins the Paxos setup, it's able to remember at least some things about what was going on before it died. And so these computers need to have hard drives or SSD drives or some form of permanent storage. The computers also need to be able to talk to each other. They need to have a network. And our assumptions on the network are actually not that big. We assume that they can send messages to each other and those messages aren't corrupted. We don't assume anything about how often those network links fail. A network link failing is quite similar to a computer failing when you look at the math behind it. And we also allow messages to become delayed and go either quickly or slowly or get reordered as they go across the network. And just again, to emphasize, what this model is, this is a fail-stop model and not a Byzantine failure model. We're not assuming that a hacker gets into one of these computers and injects the exact set of messages that messes with the algorithm, makes it do the wrong thing. What is the problem that the basic Paxos algorithm solves? The problem is that one computer proposes a value, say for example 7 or 3 in this case, and then we want one of those values to win and become the chosen value. And so the Paxos algorithm tries to propagate these values from one computer to another. In this case, the 7 managed to propagate to the computer in the top right. And the algorithm decides on a value. So these are proposed values. The algorithm decides on a value as soon as the majority of computers in the cluster agree on a proposed value. So in this case, as soon as 7 gets to 2 of the 3 computers, we can say that Paxos has chosen a value, and that no matter what happens in terms of failures, the eventual chosen value will be 7. The other thing that Paxos does is it allows the system to learn the chosen value. And so this is used to propagate the value to the remaining computers. So for example here, 7 would get propagated, and it would replace the proposed value on the bottom computer, such that they all say that 7 is the value that was chosen. So now you have not only a chosen value in consensus, but you also have redundancy because the value is propagated to all the computers. Let's dive in and look at the basic Paxos algorithm, message by message, so that we can understand how these computers can come to consensus on a single value. We're going to start by looking at basic Paxos and look at the case where you have a bunch of computers trying to agree on a single value. They're not fighting over values. We're going to start also by looking at the failure-free case. How does it work? Well, first thing you need to know is that if you read the paper divides the roles of the computers up into a bunch of named roles. You've got proposers, and these are the computers that have a value which they want to get the cluster to agree upon. Then you have acceptors. The acceptor's job is to listen to the proposals, to store what's been proposed, and when a majority of the acceptors agree upon what value is going to be stored, then that means that the algorithm is completed and that you've achieved consensus. The paper also talks about having listeners. Their job is sort of as a redundant backup storage. They just listen to what's going on, and once an agreement has been arrived upon, they just store an additional copy for more redundancy. We're not going to deal with that in today's video. We're also going to combine the proposer and acceptor role onto a single computer because that's what any real implementation would do anyways. So, message by message. The first thing that happens is that you have a proposer and it's trying to get a value accepted. Let's say in this case, the value you want accepted by the cluster is 7. That proposer needs to choose a number n. Now, n is just an arbitrary number, which has a couple of interesting properties. The first property it has to have is that n has to get bigger over time. And the reason for this is because n is used as a virtual clock. It's used by all of the acceptors to make sure that when it receives a message from any particular server, that it's getting the latest version of, or the latest round of the Paxos algorithm messages, and it's not getting stale messages from older times in the algorithm, back in the deep dark past when something went wrong. So n has to go up over time. So as I show it here, we just have a variable that goes I++. The other thing that n has to be is it has to be unique. When you receive an n from a server, that n has to be different from any n generated by any other server. As a result, the way we do that in this particular example is we concatenate the server number onto the end of n. So 42.1 means that this is the 42nd round of Paxos run on server 1. Great. So now that we have n, the proposer goes and sends that n out to all of the other servers. And it does so in a message called prepare. And all prepare is doing is effectively creating a lock and canceling any previous rounds of the Paxos algorithm. And so it says to the other servers, if you receive any messages with an n smaller than 42.1, I want you to ignore them. Also, I want you to tell me if you've heard any messages with a n greater than 42 so that I can just give up and maybe try again in getting consensus. So each of these acceptors, upon receiving a prepare message, looks at the n they were just sent, compares it to the biggest n that they've seen so far, and if the n they just got sent is bigger than what they've seen so far, they write it to disk so that they always remember what is the biggest n that I've seen, even if I reboot. They then respond with a promise message, which is just sent back to the proposer saying, I promise to ignore any smaller n's and I've saved it on disk. If the n is not the biggest they've seen, they can either just ignore it because, you're out of date, dude, or they can respond with a negative acknowledgement so that the proposer knows that they should just give up now because there's a bigger n proposer out there that is fighting with them. And the promise message contains the value of n simply so that the proposer can discard any stale messages if they get delayed in the network and show up later. If the proposer receives a majority of servers saying, I promise to accept a value from you, then it knows that it can possibly get consensus, and so it proceeds to send out the value it wants accepted by all of the servers. And it sends this an accept message, which once again contains the value of n, and contains the value it wants accepted, the 7. Upon receiving an accept message, the acceptors go and look at the value of n and see, have I received any other bigger n in the meantime? And if the answer is no, this is the biggest n, it then writes that value to disk and says, I accept your value. Thank you. And responds saying, yes, I accepted that. Now the accepted message goes out not just to the proposer, which can then count and see did a majority of my acceptors accept it, and if so, we've achieved consensus and we're done. But it goes to every server so that every other server can look at the stream of accepted messages, and as soon as they see a majority of accepted messages for a single n and a single value from majority of the servers, they can then say, we're done, and I know what the value is that this whole cluster has agreed upon. So that's the basic Paxos algorithm as executed successfully with no failures and only one server sending out a value to be accepted. Let's talk about how things fail. What can go wrong? Well, the first thing that can go wrong is that one or more of your acceptors can fail. Now, if you recall, since we have 3 servers in this example, only one acceptor can fail and have Paxos continue to make progress. So, if we, for example, fail one of the acceptors after it's accepted a value, all that happens is that the accepted messages it was going to send out don't get sent. That's okay. The cluster still is able to come to an agreement because each of the remaining servers still sees a majority of the servers saying, yes, I've accepted the value. So Paxos completes successfully. Another failure that can happen is the acceptor can fail before it manages to respond with a promise message. Well, if it fails in that case, simply means that the proposer will only see a promise from 2 of the 3 servers. And even if it only sees a promise from 2 of the 3 servers, itself and server 2, it can make progress because it only needed a majority. And so, once again, the algorithm will complete successfully, and the value 7 will be agreed upon. So it's not a problem, as long as the majority of servers don't fail. Great. What about if the proposer fails? This is where it gets a little bit more complicated. Well, the first place where the proposer can fail is in the prepare phase, when the prepare and promise message is being exchanged. And if a proposer fails at any point during that phase of the execution, all that means is that the acceptors have received a value of n, or maybe they didn't receive the value of n depending on when the failure occurred, but the acceptors may have received a value of n, which then sets the bar so that any future iterations of Paxos need to choose a larger n. And that's what will happen if another machine tries to become a proposer and sends out a value to be accepted. In this case, the value 8 is now successfully sent out by server 2, and it's now dealing with the case we just covered, which is an acceptor has failed. In this case, server 1's acceptor has failed. And it successfully gets the value 8 accepted, the algorithm completes, and we've come to a consensus on a value. A different value than was originally proposed by server 1, but that's okay, because we just need the system to come to agreement on some value. Great. Now, things are a bit more complicated if a proposer fails in the accept phase. So what does this mean if we're in the accept phase? It means that at least one of our messages with the value that's being proposed has been sent out. And so if you look at this cluster of 3, in the 3 case, as soon as one accept message is sent out, a majority of the machines in the cluster have accepted the value 7, even if the responses haven't been sent back, because server 1 is an acceptor and it just talks to itself, and server 3 has received the value 7. That's a majority, which means that if Paxos is going to be correct, then the value 7 should be the eventual result we get. But server 2 hasn't gotten it yet, and we actually haven't gotten any server to the state where it knows that this is what's happened, that we've gotten agreement. So how does this work? Well, server 1 fails, so everything that it does goes away. And then let's say server 2 comes along and says, I want to propose a new value, because I'm now going to be a proposer. So I pick a bigger n. My n is going to be 43.2. And my value which I want to propose is 8. So I send out a prepare message, and I send a prepare message to all of the remaining servers. I prepare 43.2, and server 3 responds with, I promise 43.2. Actually, in the past, I've received 42.1 with a value of 7. So this is a new wrinkle. A promise response responds either with simply the n saying I promise to ignore everything from earlier n, Or it responds with a promise saying, here is the n you just gave me, and by the way, here is the n that I've last heard with a value associated with it, so I've already promised and accepted this value from someone else. And this is where the magic of Paxos happens. So what does the proposer have to do when it receives this kind of response? A response which says, I've already accepted a value from someone else. Well, it needs to look at all of these accepted values and find the largest n, the most recent value that's been accepted by any of the acceptors that the proposer is talking to. And then it has to use that value and try and get that value pushed through so that everyone agrees on it. And this is why Paxos works, because as soon as a majority of machines in the cluster have accepted a value, it's guaranteed that this part of the algorithm will continue to push that value across the rest of the cluster, no matter what pattern of failures happens, as long as that pattern of failures does not affect a majority of the cluster. So from this point forward, the Paxos algorithm continues exactly as we've explained it before, except it's adopted a new value, and that value is 7. And so it sends an accepted message to the other acceptors saying, I'm now 43.2 and your value is 7. And then once that message is accepted, a broadcast gets sent out to all the other machines saying, I've accepted a value of 7 in n of 43.2. And we're done. Success. So let's take a breath and review. We've just gone and presented the basic Paxos algorithm and the 4 messages associated with it. The prepare message, the promise message, the accept message, and the accepted message. And we've also gone through all of the places where you could fail when you have one proposer. If one or more of the acceptors failures, the algorithm continues to work, because as long as a majority of the acceptors are up and accepting messages, it'll work just fine. If the proposer fails, there are 2 places it can fail. One place it can fail is in the prepare phase. In that case, it's as if the round of the algorithm never happened, and another proposer, when it comes alive, will simply execute the algorithm and work correctly. If the proposer fails in the accept phase, once it's already sent out some accept messages to the acceptors, then one of 2 things will happen. Either another proposer will just come alive and ignore that original value because it hadn't gotten to a majority of the servers and propagate its own value, overwriting it, and the algorithm will work successfully. Or another proposer will notice that this value has already been pushed out to some of the acceptors, and it will propagate that to the rest of the machines. And once again, you'll achieve consensus. So we've covered all our bases for the one proposer case. What we haven't covered and explained here is what happens if you get 2 proposers that try and push a value out to the cluster at the same time and they conflict with each other. And actually, I'm going to wave my hands a bit here and promise you it all works. And if you go and read the paper, they go through all of the cases and stuff like that. But the problem with any solution where you allow 2 or more simultaneous proposals is it's possible that your system can live lock. You can get 2 proposers that each get halfway through the algorithm, and then they realize, oh crud, I see someone else who's bigger than me who's been out there, so they'll just restart with a bigger n, and then the other one will restart with a bigger n, then the other one will restart with a bigger n. You get a live lock situation, and it's not that great for performance, because it'll probably eventually resolve itself, but it may not. And so, usually when people are implementing Paxos, they say, I'm really happy that the mathematical proofs show that when I have 2 or more simultaneous proposers, that I'm not going to get an incorrect result. It may just take a long time and never get to a result, but I'm not going to get an incorrect result. So I'm going to avoid the performance problem by using some algorithm to elect a single leader, a single proposer, to run at a time, and so that I don't have to really, in the real world, deal with the 2 simultaneous proposers case. So how do you go about electing a leader so that you only have 1 server proposing at a time? You can use Paxos itself. You can have a special round of Paxos where what you do is you try and get consensus on the name or the ID of a single server in your Paxos cluster. And that works. You have all the servers say, I'm going to run Paxos and see if I can get my server name agreed to as the leader. But what if that round of Paxos itself live locks? Then you haven't really solved the problem, have you? Well, you could say, well, okay, when I'm doing that special round of Paxos, I'm going to do things like slow it down. I'm going to put random time delays into different parts of the algorithm, such that if a live lock occurs, it's very unlikely that that live lock will keep on going, because the random timeouts will jiggle things enough that it will unlive lock itself and I'll get to a solution. Great. Now you put a hack on top of a kludge, and it's not the most elegant solution out there, and then you think to yourself, well, I don't actually care if my leader election algorithm is perfect. I don't care if it works in the face of network partitions and all possible failure modes. I just care that most of the time I get myself to a leader, and if it doesn't work, well, Paxos keeps on working even if you have more than one machine that thinks it's the leader. So, the bully algorithm is a really simple algorithm that helps you elect a leader, and it works in almost all cases. And so how does it work? What you do is, if you haven't heard anything from any of your peers for a while, you assume that maybe there's not a leader elected, so maybe I'm good enough to be the leader. And so you run the bully algorithm. You broadcast your ID to all of your peers. When a peer receives your ID, it responds with its own ID. And when you receive those responses, you look and say, am I the biggest one? If so, I'm the leader. Now, why is it called the bully algorithm? Well, if you receive one of these messages of someone trying to become a leader, and their ID is smaller than yours, you say, well, I'm better than them, and you start broadcasting your own ID. You run your own version of the bully algorithm, and you basically knock out the lower numbered server. And eventually, the highest numbered server will have discovered itself and will start acting as the leader and as the proposer in the Paxos algorithm. So by this point, you probably have a good appreciation of how basic Paxos works and how you can go about building one of these systems, right? Well, this is where the complexity starts to creep in. If you want to build a real system, Paxos gets more complicated. In particular, your real system probably doesn't want to agree on a single value or implement one transaction and then terminate. You probably want to implement a series of transactions so that you have a database that changes over time. And creating this usually involves creating a log of agreements. You've agreed upon one transaction, then you agree on the next transaction, and so on. And how you go about doing this is described in the paper in an algorithm called multi-Paxos, which is a fair bit more complicated than the simple 4 messages and 2 roles that we have in our basic Paxos algorithm. Also, if you're building a real system, you probably need to system administer it. You probably need to deal with the fact that some of your computers failed. You have to take them away, add new computers. You may want to grow your cluster or shrink your cluster over time. And so you need a mechanism in order to make changes to your Paxos cluster while it's alive and running, because you really want a really good uptime. That's why you're using Paxos. And so you then have to come up with, well, how am I going to do this? Well, since I already have a log of things that are going on, maybe I can add metadata to that log. Maybe I can add special transactions that say, at this point, we agree that the cluster has grown by 1 node. Or at this point, we agree that the cluster has shrunk by 1 node. And so that just adds a little bit more complexity to what you're doing. You also need to come up with a good way of naming your machines so that you can identify which machines have been added and subtracted. You're building a real system, so you need to test and debug it, which means you need to build a test harness that can not only generate the failures that we talked about, but can also reorder messages, that can test potential bugs that might be introduced, that can test on-disk corruption to make sure that your system can tolerate that kind of thing, can test network corruption, since that happens in the real world too, and it gets fairly complicated. In addition, I mentioned corruption. Corruption is more of a Byzantine failure, right? Well, yeah, Byzantine-like failures can happen in the real world, and you need to have a procedure for dealing with it, whether it's just ringing someone's pager so they come in and manually edit things, which means they need to really understand how the system works so that they can do the updates correctly, or adding checksums throughout your system or something like that to avoid corruption. You can come up with some really crazy failure modes once you allow the possibility of Byzantine failure. For example, if you get some corruption that changes the value of n on disk for one of your nodes, it may make a really big n. That works fine. Paxos will just fail around when it discovers there's a big n, and then all of the servers will restart with a much larger n, right? But what if n is int max or infinity? At that point, there is no larger n, and Paxos will just stop. Yeah, you can come up with other failures too, but basically you need to build very reliable systems that are resilient and won't have this kind of failure. And this gives you another reason to adopt Raft, because Raft not only is easier to understand and easier to implement, there are more than one implementation out there in library form which you can just go and use in your system. So let's talk about performance. You've already made the decision that you're going to make a trade-off. You're willing to throw more computers at the problem and maybe sacrifice some speed in order to get a very reliable distributed system. And, well, how fast can Paxos go anyways? Well, the basic Paxos has a limitation on its latency. Because it involves 2 round-trip messages, you need 2 network round trips. And since it involves disk writes, both when the acceptors receive a value of n and also when they receive a value to store, you have the latency of 2 disk writes. So your total performance will be 2 times your network round-trip latency, plus 2 times the amount of time it takes for your data to reach disk and be securely written onto the platters, not just hit the disk's cache if your cache gets wiped out upon system failure. Which means that your basic Paxos can't be any faster than your network, which means that if you distribute your servers around the planet in order to get better reliability, you're paying for that in performance because your network round trip will go up. Or if you use slower disk drives instead of flash drives, that will also have a dramatic impact on your performance. Now, the news gets a little bit better with multi-Paxos, because in multi-Paxos there's an optimization, which is you do the prepare phase once, and then you do a whole bunch of accept phases, one after another, for each transaction. Because if you have a single leader, you can do that optimization, which means that over time, it converges on 1 network round trip and 1 disk write for every transaction which you try and do in your system. Assuming that you don't have failures that often, because you need to re-elect a leader and redo the prepare phase every time you have a failure of your proposer. If you're doing multi-Paxos, you can increase the amount of bandwidth you're consuming and make the whole system go faster by doing more than 1 Paxos execution at the same time for each transaction. So you're effectively running your transactions in parallel. So the basic trade-off is this. You can increase reliability by spreading your servers around the world or by using more servers at the cost of more latency. You can also increase your throughput at the cost of consuming more network bandwidth and slowing your failure recovery because you need to re-execute more transactions by parallelizing your multi-Paxos and running more than 1 Paxos round at the same time. So to conclude, you hopefully understand how Paxos works and basic consensus algorithms work, and you understand that it actually is a problem that can be solved. Basic Paxos, not that complicated. Once again, it's just 4 messages. But if you do a full-featured implementation of multi-Paxos with nice system administration capabilities, that's more complicated. And Paxos was the first system to successfully solve and provably correctly solve the consensus problem. But if you're trying to build a real system today, I recommend that you go and you learn about Raft.